Okay, so we finished up that last example, and I didn't tell you on the last example to do this, but we figured up how to find those percentages. So we had the two percentages on the last one. We had the percentage for the 63, the copper 63, and the percentage for the copper 65, and then those are right up here. And so what what I should have told you guys to do is I should have told you to try the next example on your own. So let's do that. Pause the video and try this example 3, and then I'll go ahead and work that one with you. So go ahead and try that one, see how you do. Okay, so hopefully we went through and took care of this one. It's pretty straightforward. We got a boron 11 and a boron 10. So we'll take a look at that. So first thing we're going to do is hopefully we identified that this is a percent abundance type problem, because it says to find the abundances of the two isotopes. So that's kind of straightforward. So we got two isotopes. So let's take the big one, which is the 11. And so let's go ahead and take 11, which is the big one, multiplied by x. Okay, put that in brackets if we want. And then let's add that to the small one, which is 10. And we're going to multiply 10 by 1, or 100%, 1 minus x. And then we're going to set this equal to whatever the periodic table value is for boron. Okay, so notice on this one, they didn't give us the periodic table value. We have to look that up. So let's go ahead and look at boron, and that's 10.81 on your periodic table. So you should make a note that I got this value. Where did I get this? I got this from the periodic table. Because you will probably forget that, even though it's like right now, you're like, oh, that seems super straightforward, but you're probably going to forget it. So having that as a little note to yourself, I think is a good idea. So we get that from the periodic table. It's not particularly hard to find. So we're going to go ahead and do that. So let's go ahead and run the math through. And the math is a little bit easier because the numbers are smaller, right? So we're going to have 11x. And then we're going to add that to 10. 10 minus 10x. And that's going to equal 10.81. Okay, so then we can clean up the x's. So you got 11x and you got negative 10x. So that's just going to be x equals. And then subtract 10 from the right side. So we'll go ahead and subtract that 10 from 10.81. So if we go ahead and do that, we're going to get 0.81. Okay, well, that kind of solves it for us, right? It's like, okay, here you go. X is going to be 0.81. What does 0.81 mean? Well, that means 81%. So remember that the bigger value, the 11, is what the x is going to be. So 11 is going to get the 81. So what that means is that our boron 11 is going to equal 81%, and the boron 10 is going to equal, now how do we figure that out? Pretty straightforward. We're just going to take 100 minus 81, and that's going to give us 19. So that boron 10 is going to be the 19%. So really the key thing here is to remember that the larger value, the 11, that's what was the x. So the 11 is going to come from the x, and then the remainder, the leftover, that's going to be the other, or the smaller one. So we have the one that's heavier, that's the X, and the lighter one, that's going to be the remainder. And so if you can just remember that we set the heavier one with the X, then that would be good. So maybe we'll make a little note here that the X was heavier. That was the, can't spell that. There we go. That was going to be the heavier one, or in this case, the 11. Okay, so hopefully that'll help you out. I think that they're pretty straightforward. This one's obviously a little easier than the last one. So, all right, hopefully you did well on that. Okay, mass spectrometer. I think this is going to probably this might look a little bit different in the notes I gave you because I modified this a little bit. I got a nicer picture for this year. So I think that you've got the one before I changed it, but that's okay. So this is a mass spectrometer, and it's a tool. So it's a device. So like an electronic balance or something like that. It's a tool. And so what that tool does is that it takes an unknown sample, and it tests that sample by seeing how the parts of the sample are affected by a magnet. So if we read the definition, it says mass spectrometry is an analytical technique used to measure the mass to charge ratio of ions. It's generally used to find the composition of a sample. So this is sort of the first key thing that we're going to use it to find the composition of a sample. So think about like a show you've watched on TV. So maybe it's like a forensic science type show, a CSI or some kind of crime show. Well, they might find something, a piece of evidence at the scene, and they take it and they give it to the crime lab, and the crime lab says, "Oh, it was one of these two types of paint, or it was a piece of plastic that's only found in these particular tennis shoes," or whatever. Well, how do they have any idea what that mystery item was? Well, they probably put the sample into a mass spectrometer. And so what happens in a mass spectrometer is that you put your sample in at the beginning. So we're going to put it in here. And what happens is your sample gets turned into a gas. So when it says vaporize your sample, what they're saying is that we have to turn the sample into a gas. So they put the paint chip in, or the tiny piece of tennis shoe or whatever, and they basically melt it and then turn it into a gas, add a bunch of heat. So in here goes the piece of the tennis shoe. And then tiny piece, and it gets turned into a gas. And then what happens is it gets accelerated. So they speed up the particles going in this direction. And when they hit this spot right here, what happens is there's a magnet. And so what the magnet does is that it takes the particles and it pushes them. So the ones that are the lightest are going to get pushed the most. So that should make sense to you. Light things should be able to be pushed the most. And so what happens is they push those particles. And so you can see here, this one is the lightest one because it got pushed the most. And this is the heaviest one because it got pushed the least. And then what happens is they come down here and then they hit down here on this detector. And by doing that, they create some data. So when we get a color, we can actually see. So they come down here and they would be hitting down here in this spot, and then over here and over here. So be hitting in all these spots, and you'd be getting all of these things hitting the detector. So what happens, the detector looks at the data, looks at the mass values, looks at the types of things that are put in there, and it runs it through a computer database, and it says, oh, this was these chemicals, and these chemicals are found in this paint or in this type of plastic, which is used in these tennis shoes. And so the device is usually hooked up to a massive database, and then that database says, okay, this is what your chemical was. So anyway, we do not have one of these because they are extremely expensive, but that's how it works. So what is a mass spectrum? This is what you need to know for the test. a mass spectrum is going to be what the detector spits out. So the detector is going to create a mass spectrum, and then that's what the computer basically analyzes. So it says when you look at the spectrum of an element, the various isotopes, so let's put that here, the various isotopes, and their natural abundances are shown. So when we look at one of these mass spectrums, which we'll look at a bit, you're going to see the different masses. So you have different masses or different isotopes, and you're going to have their natural abundances. And so you can either look at them graphically or there might be a percent. Okay, so these abundances, they could be represented graphically or with a percent. If they're graphically, you'll have kind of a graph that looks like this, and you'll have some highs and lows, something like that. So we'll look at that here in a minute. It's not really that complicated. It's actually pretty easy for what we have to do for IB. So, and then it says the last three blanks here, it says the relative, or you could think average, either way, the relative atomic mass or average atomic mass can be determined from your graph. And then, like I said, the other word we use for this would be average. So both of these are the same thing. And so basically you can get this graph. And so you're going to have this graph here. And then if you have like a line here and a line here and a line here, then it might have the masses. So up at the top, it might say, well, this one weighed like 56, and this weighed like 57, and this weighed 58. And then these lines would come over here, and we could look at some percentages. So maybe let's say like this is 25% and this is 50%. And so then we can do some math and kind of figure out what our mystery element is. So that's kind of what's going to be going on here. So, all right, so slide down here. Oh, sorry, go to the next one here.